Hello. Now that we have this simple example that just shows a number as hexadecimal, let's make a 64-bit version, starting from scratch. We need to use format PE64 to make a 64-bit executable, and let's just put a breakpoint here. You should notice that now we have 64-bit registers, twice the size of 32-bit ones that we've been using, and they have names starting with letter R, like RAX. Therefore, now we can use 64-bit registers. For example, load a huge number into such register. Skip the breakpoint, execute the move instruction, and this number has been loaded into RAX register. We can also still use 32-bit EAX, which is just the lower half of this 64-bit register. So let's see how this works. First we have this huge number loaded into RAX, and now we load 8 digits into EAX. And you can see that the upper part of the RAX register has been zeroed. This is something specific to 32-bit operations. For example, if we try to write only 16-bit register, or even 8-bit one, then, as you can see, the upper portion of the 64-bit register remains. It is not changed by these instructions. However, when we modify EAX as a whole, when we perform a 32-bit operation, then the upper portion of 64-bit register is going to be zeroed. This means that to put a smaller number into RAX, for example 1, we do not really need to use 64-bit operation. We can do it with mov EAX1, which has the same effect, but it is a shorter instruction. This is often useful, and in general we need to keep in mind that an operation on a 32-bit register is going to zero the upper portion of corresponding 64-bit register. As for the 64-bit operations, other than mov, they have a limitation that if there is a number directly in the instruction, a so-called immediate value, then it needs to fit in signed 32-bit range. So for example, we can add 1 or -1 to a 64-bit register, but we cannot add a huge number like this one. This cannot be encoded correctly. Therefore, in this case, we would need to use some register temporarily to store this number and perform the addition. It helps that we now have more registers. As you can see here, we have 8 additional 64-bit registers from R8 to R15. And we can use all of them exactly the same way as the classic registers. For every one of them, we can also use a 32-bit portion of the register by attaching the letter to the name. And 16-bit portion is going to be R8W. And a single byte, the lowest byte of the R8 register, is then R8B. Also, we can now access lowest byte of a register like SI or DI, which was not possible before. On the other hand, in the new scheme, there are no higher byte registers like AH. We can still use both schemes, but we cannot mix them. So if we use one of the new registers in an instruction, then we cannot use an H register. It is not possible to encode such instruction. Now that we know the basics, let's move on to the example. And we are going to copy the entire import section. It only needs a small change. The table here has 32-bit entries, and they should be 64-bit now. So we need to change double words to quad words. DQ is going to define quad word, 64-bit value. So now we are going to have 64-bit addresses to the functions. And to exit program, we need to call exit process function. But this is wrong because we have a different calling convention now. 64-bit Windows uses fast call convention, where the first 4 arguments are passed in registers in RCX, RDX, R8, and R9 registers. In this case, we need just a single argument, so it is going to be RCX. And as we know, we can use a 32-bit operation to set up entire 64-bit register. But this is not enough. We also need to reserve space on the stack for the 4 arguments. This is because the function may want to have all the arguments on the stack, and it may just store these 4 registers on the stack for various reasons. Therefore, we also need to move the stack frame RSP register so that we have a space reserved on the stack for the 4 arguments. Every 64-bit value is 8 bytes. So this is the size of 4 64-bit registers on the stack. And we can reserve space for even more arguments, because with fast call convention, the function does not restore the stack frame. So once we reserve space, we can keep it this way for multiple function calls, and we can just reserve once as much space as we may need to call any function that we plan to call. And there is still another issue, the issue of alignment. For performance reasons, fast call convention requires that the area on the stack for the arguments is aligned to 16 bytes. That is, the address must be a multiple of 16. In hexadecimal, when the number is a multiple of 16, it has the last digit 0. So we can check this alignment now in debugger. We need to look at RSP register, and as you can see, it initially is not aligned. The last digit is 8. This is because of the return value that is put on the stack. Then when we modify the address by subtracting a number that is multiple of 16, the stack is still going to be misaligned. So we need to correct this. We need to add additional correction for this initial misalignment. And now if we put a breakpoint here, we can check that the stack now should be aligned properly and with space reserved for many arguments for any function that we may need to call here. RSP has now the last digit 0, so it is aligned properly for the function call. And this should be working, not crashing. Next, let's try a message box function, which has 4 arguments, so all of them are going to be in registers. The first one can be 0, and the last one can be 0. And the middle ones should be the text and caption of the message box, so we need some text in the data section. We can copy from the example and add a terminating 0 here. We are going to use the instruction load effective address, because this is the best method of loading a 64-bit address to register in 64-bit mode. Instead of loading a huge number, 64-bit number that is an address of something in the register, we can use this instruction that has the address encoded as just a relative offset from this instruction to the place in data section. And as you can see, this is working correctly. And finally, let's convert our function. Starting from the top. All pointers are now 64-bit. And we also need to keep stack aligned because we want to call a system function later. Initially, we have return address from the function stored on the stack, which is 8 bytes. So initially the stack is misaligned, but then we store another 8 bytes by storing RBP on the stack, and it becomes aligned to 16 bytes. So to preserve this alignment, we need to subtract a multiple of 16. So we simply need to allocate a local area of a size that is a multiple of 16. we are going to use the same address in a few other places. We also need to allocate space for function arguments, because we are going to call function later. So we are going to allocate space for 4 arguments for the message box. We could allocate more if we wanted to call some other functions that would need more arguments. Next, we have a list of registers that the function may destroy. These are now 64-bit registers, and we can add R8 and R9 to the list, and also R10 and R11 per convention. These are now 64-bit pointers, and because at this address we have stored 8 bytes of RBP register, the return address of the function is at RBP plus 8, and the first argument would be at RBP plus 16, but the first argument is passed in register. It was not stored on the stack, so instead we can take it from the register, and let's take all 64 bits of it. Now, we cannot simply push a register on the stack to preserve it, because we would misalign the stack at this point. We can simply use some other register that does not need preserving here. So instead of EBX, we are going to use, let's say, R10. And this is a pointer, so it needs to be 64-bit. Okay, it has been replaced in all places. Here we are going to use RAX as an index into array, because the base address may be 64-bit. And we can do it safely, because after this 32-bit operation, the upper bits of the 64-bit RAX register are zeroed anyway. Now, to call the message box, we need to put the arguments into registers. So first one is going to be zeroed. The last one is going to be zeroed. And we are going to use this address as the second and third argument. This should be RBP. And finally, we do not use this argument to return, because in this convention the function does not restore the stack frame, so it just returns with plain return function instruction. We can try to call our function now. And it worked correctly. Finally, we can modify the function to show 64 bits instead of just 32. So here, where we start from the highest nibble of 32-bit number, we can start from the highest nibble of 64-bit one, and then shift 64-bit register to get the nibble, and we can follow as it were. but we need more space for the text because it is now going to be longer. So we need to increase this allocation. And it also needs to be a multiple of 16 to preserve the alignment. So let's allocate 32 bytes as the local space. And here we can just duplicate the value. Okay, it seems to work. Let's test it with a full size number. It works. So now we have a complete 64-bit version of our example. Thank you for watching.